This video will definitely give you detailed information on stars. All you need to make a star is hydrogen, dust and gravity. Stars are made of gas basically, and our galaxy has gas. In fact, our galaxy you can consider is of gas and dust that surrounds all the stars, and from this gas the new stars are born. Stars are those objects that can produce more than 1000 times energy of sun and can be 100 times massive than sun. In fact, the Sirius star can outshine our sun more than 20 times. But how are they formed? By observing the evolution of nebulas at different stages, the story of the stars becomes to rise. Stars are the most widely recognized astronomical objects and represent the most fundamental building blocks of our galaxy. The age, distribution, and composition of the star in a galaxy trace the history, dynamics, and evolution of the galaxy. Consequently, the study of the birth, life, and the death of the star is central to the field of astronomy. Stars are born within the clouds of dust and scattered throughout most galaxies. A familiar example of such as a dust cloud is Orion Nebula. The turbulence within these clouds give rise to the knots with sufficient mass that the gas and dust can begin to collapse under its own gravitational attraction. As the cloud collapses, the material at the center begins to heat up. The material that is at the center is known as protostar. It is this hot core at the heart of the collapsing cloud that will one day become a star. The interesting point to note is the stars are those objects. When they are born or when they are dead, they produce so much heat that they can wipe out our entire civilization at once. Interesting to know that, yes. Where were we? Yes, how the stars are formed. I got diverted from the topic. As the cloud collapses, a dense hot core forms and begins gathering dust and gas. Not all the material ends up as a part of a star. The remaining dust can become planets, asteroids or comets, or may remain as a dust. But what are the main sequence stars? A star the size of our sun requires about 50 million years to mature from beginning of a collapse to adulthood. Our sun will stay in this mature phase on main sequence star as shown in Hertzsprung-Russell's diagram for approximately 10 billion years. Stars are fueled by the nuclear fusion of hydrogen to form helium deep in their interiors. The outflow of the energy from the central region of the star provides the pressure necessary to keep the stars from collapsing under its own weight and the energy by which it shines. As shown in Hertzsprung's Russell diagram, main sequence stars span a wide range of luminosities and colors and can be classified according to those characteristics. The smallest star, known as red dwarf, may contain as little as 10% mass of the sun and emit only 0.01% as energy, glowing feebly at temperatures between 3000 to 4000 Kelvin. Despite their diminutive nature, red dwarf stars are far the most numerous stars in the universe and have lifespans of 10 of billion years. On the other hand, the most massive star, known as hypergiants, may be 100 or more times more massive than Sun and have surface temperature of more than 3000, not 3000 but 30,000 Kelvin. Hypergiants emit hundreds of thousands of times more energy than Sun but have lifetime of only few million years. Although the extreme stars such as these are believed to have been common in early universe, today they are extremely rare. The entire Milky Way galaxy contains only handful of these hypergiants. In general, the larger a star, the shorter its life. Although all must be the most massive star live for billions of years. When a star has fused all the hydrogen in its core, nuclear reaction ceases. Deprived of energy production needed to support it, the core begins to collapse into itself and becomes much hotter. Hydrogen is still available outside the core, So hydrogen fusion continues in shells surrounding the core. The increasingly hot core also pushes the outer layers of the star outward, causing them to expand and cool, transforming the star into a red giant. If the star is sufficiently massive, the collapsing core may become hot enough to support more exotic nuclear reactions that consume helium and produce a variety of heavier elements up to iron. However, such reactions offer only a temporary reprieve. Gradually, the star's internal nuclear fire becomes increasingly unstable, sometimes burning furiously, other times dying down. These variations cause the star to pulsate and throw off its outer layers, the enshrouding itself into a cocoon of gas and dust. What happens next depends on the size of the core. For every star like the Sun, the process of ejecting its outer layer continues until the stellar core is exposed. This dead but still furiously hot stellar cinder is called a white dwarf. White dwarfs, which are roughly the size of our Earth despite containing the mass of a star, once puzzled the astronomers. Why didn't they collapse further? What force supported the mass of the core? Quantum mechanics provided the explanation. Pressure from fast moving electrons keep these stars from collapsing. The more massive the core, the denser the white dwarf that is formed. Thus, the smaller a white dwarf is in diameter, the larger is its mass. These paradoxical stars are very common. Our own sun will be a white dwarf billion of years from now. White dwarfs are interestingly very faint because they are so small and lacking a source of energy production. They fade into oblivion as they gradually cool down. This fate awaits only those stars with mass up to 14 times the mass of our sun. Above that, the mass electron pressure cannot support the core against the further collapse. Such stars suffer a different fate as described so much again and again. A star like our Sun has a lifetime of about 10 billion years and is just middle aged with another 5 billion years left or so.